My real pleasure to introduce this afternoon's plenary lecture, Mohy Mansour. We all know him, of course. He chaired the local organizing session for this, and so I think we should give him a hand of applause for yesterday's fantastic tour. So thank you. That was very much enjoyed that. So Mohy received his PhD from the University of Sydney in Turbulent Flames. Then he returned to Cairo, where he had gotten his undergraduate degree, rose through the academic ranks to full professor, before leaving to join American University of Cairo in 2000, where he stayed until recently, 2022. During this period, he also served as the Dean of Engineering at Beni Suef University, and he has now recently returned to University of Cairo as an emeritus faculty. He's chair of the Egyptian section of the Combustion Institute, as well as a fellow. We look forward to your talk on flame stability. Thank you.
Thank you very much, Robert, for this nice introduction. And before I start, I would like to thank everybody for coming here. I hope that we provide you with all help and support, and by the end of this conference, I hope that everybody's happy from science and culture and whatever you have. So my talk today is about combustion stability, which is a term that actually everybody is worried in. When we design our system of combustion, we need to stabilize the combustion to provide better environment for flame stability, as well as less production of pollutants from our system. So when we're talking about combustion stability, this term actually refers to be affected by many factors, and one of them is a mixing field structure and the flow field chemistry and heat supply or heat transfer, and also the system design. So all of these parameters contribute to the stability of the flames and combustion. So I will not go through all of this, of course. I will just focus on one very important aspect in this combustion stability, which is the mixing field, and how does it affect actually the flame structure and the stability of the flames and combustion system. This work, maybe I've been working on that for maybe more than 25 years or more, and I focused more on this point of stability or the mixing field. So if we classify the combustion modes, we have two extremes. One of them is called premixed, and the other one is actually non-premixed. In the premixed, we have a certain value of mixture fraction and constant, and in the non-premixed, we have two streams. One is actually pure fuel, one is pure air, and then we have a diffusion mixing. In between of this, we have actually a very wide range of structure. People call it inhomogeneous, and some people say partially premixed, and some call it stratified. So I will lump them, all of these in one word, IPPS, which is actually inhomogeneous, partially premixed, stratified, because whenever you design the system, you may end up in some part of the system which is actually covering one of these or all of them together. So this is actually have a wide range between minimum and maximum mixture fraction, and you may have end up to buckets of that. So back to 1985, when I started my PhD with Professor Bilger, I went to this actually very noisy burner called reverse flow reactor. And his idea is to create actually some stratified and partially premixed here by injecting some fuel in the middle, and with this nozzle hitting a cup in front and actually having some kind of recirculation zone here. And this flame was actually very strong, and we could reach up to 200 meters per second of jet velocity, and imagine how noisy this flame is. And then when I went back, we started to build this actually concentric tube burners with actually the inner tube carrying air, the outer tube carrying fuel, and we also surrounded with some pilot, and that was the work of my PhD student at that time. You can actually have a lifted flame of that. You can stabilize, attach it to the nozzle. There is another work by Lee in 1997 with almost quite similar configuration of a multi-tube system. And then we added another stabilizer, which is a cone on the top of this nozzle, and that enhances the stability quite a lot due to the aerodynamics of this flow. And then we also have another burner from Sydney University, which is having the same philosophy and the same idea. For actually this multi-tube, we have seen some paper this morning about this. So we have fuel in the middle and air in the outside, and pilot flame to stabilize this. So you can have, you can stretch the flame and have very nice flame structure as well. Kaust also, they have some kind of a new burner called double swirl, where also one of the outer has a different equivalence ratio than the inner, so this is stratified. And we went further in this, and we wanted to enhance the turbulence level inside this tube by adding the Centevica turbulence generator, so we can increase the turbulence level to 30–40% instead of this turbulence from normal jet flow. And also we have this Darmstadt burner with multi-tubes with you can design that with different stoichiometry and also stabilize the flame. We moved on one step further by replacing the circular type of a nozzle to slot type of nozzle. So the idea behind that, I will explain that in the next slides, to have a better stability and to get rid of the effect of the curvature of the nozzle itself and end up with a planar flames. It looks nice like this. So you can have some nice planes here. And this is the front view, this side view. And you can also have some lifted flame from that. So this is just some fundamental burners everybody of us wanted to understand or to create these flames for stability and come close to some practical conditions like the engine, like diesel and gas turbine system and so on. Back also to look at stability characteristics. This is a nice stability curve between the jet Reynolds number for also IPPS flames, where we have the length of the tube or the mixing length over diameter is 25, and we vary with the equivalence ratio. The nice thing about this diagram, it shows that this region here is attached flame, and if you stretch, it does not lift until you hit this line, then it starts to lift. But if you burn the jet from downstream, then you end up to lifted flame. So this area is either lifted or attached. It depends where you ignite your flame. And if you also go through this line, this is what we call blowout from lifted, and this limit here is blow off from attached. Then we said, how about if we change the mixing level? Does this change? Yes, it does. So if we have reduced the length to L/D=1, then we get this kind of shape, and then we moved on L/D2 and 4 and 6 and 8 and so on. Then you can see the structure or the stability curves, they are moving with this. So that means the type of mixing or the level of inhomogeneity in the jet affects this kind of behavior. And if we plot this point A versus L/D, we can see this is moving like this. So this is a point which is moving, which is separating these different sections. Also, we did some study about the flame kernel propagation in also IPPS jet, and we could observe this with 2D cameras, one looking at Rayleigh for temperature, one looking at OH. Then we followed the speed of the flame propagation at different L/D for the same conditions. You can see the change according to this variation of degree of partial premixing. Also the recent work of the group in Kaust about this double swirl burner with ammonia percentage. You can see also the effect if they have the outer swirl jet, which is phi equal 0.5 or 0.6 or 0.4. So the stability is shifted according to that, and we have also another limit for flashback. So this recent work from this group. If we go back again and look at some fundamental flames, which is actually what we call it edge flame or triple flame structure in laminar condition, where we have rich jet in the middle, lean in the outside. So you can stabilize the flame in this format with what we call a triple edge here with lean, rich, and diffusion flame. Does this structure exist in the turbulent case? Yes, we did some measurements with 4 cameras looking at Rayleigh OH and laser-induced precision of OH and BAH and also formaldehyde. Then we could observe the 3 reaction zones, and also they are all connected at one point. And this shows that yes, we do have this kind of structure, ring structure stabilizing even turbulent flame. So stabilization for this type of flame is actually very much related to this stuff. How about the mixing field? This is actually the line of stoichiometry, and if we follow this line and follow these 3 reaction zones, you can see actually the stabilization point exists in the vicinity of this stoichiometric mixture. And if we take the average even, then you get also the same point connecting on the average basis. So we can look at different flames and the lift-off height and how also the mixing field looks like below this stabilization point. And these are different actually shots showing the same trend. If we go further and look at the stability of this concentric flow, conical flow burner, so we can plot the Reynolds number versus L over D, which represents the degree of inhomogeneity, and for different equivalence ratio. And we observe some nice structure here for methane and for propane, for hydrocarbon flames. You can see that actually it shows that the stability is low if you are less actually in homogeneity, and the stability is even low even at high L over D where you are close to premixing. So either premixing or non-premixing, they are less stable than a certain level here of inhomogeneity, which has a peak of maximum stability. This is the case for propane and for methane. Same work was done in Sydney and showing the same trend. We have seen that also this morning. You can see that we have a peak stabilized point, which it definitely has something to do with the structure of the mixing in this part. We need to move on from physical space, L over D, to mixture fraction space by actually doing some measurements about the mixing field, looking at the minimum maximum value from the BDF of the mixture fraction, and then we converted from L over D to delta Z. And then we could see that the high stability point here for methane flame is around this actual delta Z value and delta Z value. We went further by normalizing this range of mixture fraction fluctuations by the flammability limits, where this R delta is normalized by the difference between rich and lean flammability limit, and we could see that the high stability here exists almost at the same level of flammability limit, and here is around 0.4 of flammability limit for propane flame. So what does it tell us? What can we extract out of this? That we can optimize the stability by controlling the level of inhomogeneity in the mixture. And if we go further in this type of flame, we can actually look at flame without actually co-flow. We added co-flow to the flame at 5 meters per second, and further co-flow of the flame to actually 10 meters per second. And this really enhanced even the stability. But this is aerodynamic enhancement, not actually mixture fraction distribution enhancement. So this is actually the improvement you can get by adding higher co-flow velocity. So you can move on with this curve upward here by moving from 0 to 15 meter per second. And this is very good for practical combustion system or burners. And normal burners, you have a co-flow or you have a blower, so you can stabilize even the flame further. We also did that. We have an industrial burner here in Egypt, which is actually working on this burner, and it's really very good and highly stabilized. It has been working for about more than 15 years without any problems. Something just during the lecture, I was looking at the pyramids, and one interesting coincidence between this design and the burner, that this angle 52, which for coincidence it's the same angle of that cone. That means the pharaohs gave us some idea about stability. Okay, so by adding this turbulence generator, we should be able to stabilize the flame, but how much that affect is not really much affecting the increasing the turbulence on this actually part. So this is one disc which has a certain diameter of this. This is actually slot of 1 millimeter thickness, and we vary this diameter. So this is with one diameter, and this is another diameter which has higher stability. So if we combine that, we don't see much difference, maybe slight increase by changing this. Okay. This work also was done in 2000, looking at the same burner but different diameters. We found that by increasing the diameter of this burner, the stability is enhanced. That means it's actually affected by the curvature. So we wanted to move away from this effect. We need actually to have a flame which is not affected by this curvature. Then we said, okay, if we have infinite diameter, means it's a flat and a slot. So that's why we change it from circular burner to the slot burner. And this is one model of this slot burner, which has a hydraulic diameter of about 15 millimeter. And then we have another model or another version of this burner which has a larger hydraulic diameter to increase the Reynolds number. And also we added this kind of conical shape system to stabilize the flame, which also it has very good effect on the flame stability. This is the stability of that burner, which is showing also similar trend, but it's not that sharp like the conical type circular burner. It goes to some kind of a flat curve here on that right part. This is versus L over D. Also, we wanted to convert that to mixture fraction space. So that's actually in mixture fraction space normalized by the range of flammability limit. And looking at this maximum point, and if we plot this maximum point for different co-flow velocity, you get this structure. So it's nice looking at stability, but now we need to find a link between stability and mixing field. So we went and did some measurements in Sydney, and did some measurements in Aachen to look at some mixing field structure. So these measurements actually from Rayleigh measurements in the slot burner, and looking at the mixture fraction distribution and also the gradient. What's interesting is, does the equivalence ratio is the main factor that affecting the mixing field, or the velocity ratio between the air and fuel? So it's actually turns out that the velocity ratio, that's why we made two designs of this burner by changing the area. So this area for one version is 1 millimeter, 6 and 1, and another version 2, 4 and 4. That means the area ratio changing, so the velocity ratio will change. And this is actually the diagram showing that the velocity ratio is increased here from burner A to burner B. This one is 161 and this is 242. And you can see definitely the change of the mixing field structure by changing the velocity ratio. So we said that now later on when we try to analyze our data, we selected the velocity ratio rather than the equivalence ratio. So what about density? Density also has an effect. So if we use momentum ratio, maybe also it's better than using actually velocity ratio. So these are different cases here. and at different L over D, 2, 3, and 7. Of course, at 7, it's more mixing than at 2. And these are the diagrams for the stability curves, actually, for different velocity ratio. So you can see that with smaller velocity ratio, it has higher stability than higher velocity ratio. So this is actually burner A and burner B, and if you combine them, you get this, and if you combine and change from L over D domain or physical domain to the mixture fraction domain, then you get this kind of stability curves. So this is again another case where the same equivalence ratio but different velocity ratio and momentum ratio, okay? And this is the same and so on. If we talking about using low calorific value fuels or biogas or new renewable fuels, which usually has low calorific value, and we all know that stability of these flames are much less than the normal methane. But let's say, can we use a technique to enhance the stability of these low calorific value flames? So we try to do that. So in this actually tests, we change here the fuel in the middle and the air in the outside, and we actually made some plot for different cases with 0 CO2%, 10, 20, 30, and 40. And you can see actually the variation of the stability with the momentum ratio here. But what's interesting is the next curve. If we look at that at certain L over D, which represent the maximum or the highest stability for different CO2 ratio, we see slight change, not that much change. It means what? That if we use another technology, we can even stabilize these low calorific value fuels better. And that's actually a very nice conclusion from this work, that we can really design our system for higher stability of these low calorific value flames without problems. So that's the story of the stability. Now we need to go, how can we describe the mixing field better in order to understand the link between the stability and the mixing field? Please remind me how much time is left. Okay. So we started to look at the mixing field. This is LES by Professor Bai from Lund, looking at this burner and looking at the mixture fraction distribution within the tube. And we cut at certain L over D, and then we can compare that with our measurement. This also the mixing field with the streamlines showing actually the entrainment of the air, and we have some kind of recirculation here zone at the bottom of the. By the way, these flames, this is a circular type, not the slot type, are almost lifted with about 3 millimeters from the tip. So it's not really attached to the nozzle. It's actually stabilized at about few millimeters from the exit. Then the first set of measurements, as we did before, this actually at the nozzle exit, looking at the mixing field structure by changing L over D, and by changing Reynolds number, by changing equivalence ratio, then we can have some kind of a data. How do we do with this data? So this is actually looking at mixture fraction distribution and the gradient, 2D gradient of this mixing field. We can do BDF, yes. From the BDF, you can say that here at L over D of 0, of course, we expecting to have bimodal distribution with fuel and air. And by increasing L over D, this becomes actually more mixed, and then the BDF becomes steeper like this. And the gradient also will change. And if you change the equivalence ratio, you get this kind of structure. And that's nice. And then you can actually have this BDF for each shot, and you combine them together to look at the fluctuations of this BDF. So it can tell us something, and we can also find correlation between these RZ, which is actually normalized mean value of Z divided by the average of Z reach and Z lean, we could find actually, or we could obtain some kind of nice correlation here between this RZ and VR. This should be VR in both axes. Then we went one step further by trying to create what we call it actually 2 axes and 3 axes mixing field diagram. If we look at any part of this, like if we grab this one here on 3D scene, you can see this kind of structure, and you have some point here which has maximum gradient. And if we go through this line and trying to plot the mixture fraction profile in physical space, that's what you get between minimum and maximum. And you have a point which has a maximum gradient. And if you draw a line of this maximum gradient, then you intersect Z mid, Z min, and Z max at 2 points. Between these 2 points, we may call this is actually the mixing layer. And this is a mixing layer thickness, which is mixing between the max and min. Okay? Now, let's convert from physical plot to physical space plot to mixture fraction space plot. And this is what we can get. You can actually start from here to there. Then you have a minimum dz by dl. You go to the maximum, which is this point, and then you go to the minimum again. Then we said, let's change our selection of minimum and maximum from BDF we got before. Now we can use this one to get our Z min and Z max. And use this dz by dl maximum. And this actually will be some characteristic dimensions to plot these 2 axes diagram, and then we plot the 3 axes diagram, as I'll show you later. So from here on the left side, this is one cut from that diagram, and this is a gradient of this cut in this physical space. This is about 5 by 5 millimeter or so, and this is on the left side is a mixture fraction. On the right side is a gradient of this mixture fraction. So if you do several cuts through one image, then you can see that that's actually what we actually got from this diagram here. You can see these structures, and you can actually, from each profile, you can get minimum and maximum, and you can get dz by dl maximum. And you can see how this L over D affects this kind of profiles. From L over D3, you are on the right-hand side with wider range of between minimum and maximum, and higher gradient by increasing the L over D. That means you have more mixing. Then you move to the left with lower gradient and less distance between minimum and maximum. And that should be very useful to characterize our system. And this is just the same graph we presented before to show for different equivalence ratio from to lower. Okay, and you can see how the structure changing from L over D2, 3, and 7, and how the BDF they look like. So the first 2 axes diagram, we selected this ZMM, which is the average between maximum and minimum, and delta Z, which is the difference between maximum and minimum. And then we normalize this by actually the ZR and ZL, which is reach and lean, the average and the difference between these two. Then we could actually plot this diagram. On the axis X is Z delta ZMM, on the axis Y, ZMM. And then we can see this axis, which has 0 delta Z, that represents the pre-mixed stuff. And this point is only one point representing the non-premixed stuff. And if we plot different lines like Z minimum equals 0, and Z minimum equals ZL, and Z minimum equals Z stoichiometric, you get these kind of lines. And also if you plot Z max equals ZL, you got this kind of actually boundaries, as we can say. And this actually one here, which has this IPPS within the flammability limit, and the other is outside the flammability limit. If we get a full picture, this is a full picture, where we have one point representing the non-premixed and one line representing the pre-mixed, and every point here representing that actually. And where are we? That will determine how the flame structure should look like. And this is for methane, for example. And then if you normalize by the range of mixture, flammability limit and the average flammability limit, then you get this kind of diagram. So I may skip that. This is just explaining every region in this diagram. Just quickly showing that. So we end up to different, actually, regions. Each one has some characteristics from fully premixed to non-premixed, and then different regions here, 8 regions you can classify. And these are data for different fuels. So that's the diagram you can get, but we got this diagram using actually the Zmin and Zmax from the PDF of the mixture fraction, not from that profile. And we could see some changes, the effect of equivalence ratio on these fluctuations or scattering. And also here we can see the effect of the Reynolds number. And we published many papers actually out of that from this kind of structure. Now, we said this is not enough. This will not tell me the whole story about the mixing field. We have something missing. What's missing is the gradient. Gradient is a very important parameter in mixing. Then we added another axis, which is actually dz by dl. So this is actually the new diagram, which has delta z, zmm, and dz by dl. So we can expect to have boundaries also for these 3 axes. This surface represents zmin equals 0, and the other surface, which is actually represents z maximum equal 1. So let's see the picture now. The color code represents dz by dl. So red and the black is the highest one, and the red is the less one. So this is actually showing that we have higher gradient on this side and lower gradient in this side. That's zmm, and that's delta zmm. So if we do it 3D or 3 axes, that's what you can see. So on this diagram, we are plotting every point which represented by one profile. So from one image, we can get thousands of these profiles. And then we can actually, maybe from 500 shots, we can get hundreds of thousands of these points, and then we can have a full picture about the mixing field. This is a laminar flame at L over D of 2 and phi equals 4. So you can also have 1 projection from this side, 1 projection this side, 1 projection this side, and the 3 axes diagram. These are the boundaries of these axes, or of this diagram. So if you plot, or you take this projection, dz by dl versus delta zm, we can see one boundary here, and then scattering somewhere. If we plot dz by dl versus zmm, we can see this kind of pyramid structure, which actually showing that the range of zmm is decreasing while you are going up in dz by dl. So let's compare cases. Now the first one here at the top showing the effect of L over D in laminar cases. So this is the L over D2, L over D5, L over D10. Of course, by increasing mixing, we're expecting actually this to shrink and dz by dl to be reduced. Okay? And if we plot the 2 axes, then that's actually how does it work. So this is actually moving from this side to this side, and then you can see that it's going to be touching this line where L over D of 10, probably if you go to L over D 25 or 50, so that will be pure pre-mixed, and that should stick on this vertical axis. If you plot this actually dz by dl versus zmm, then you get this kind of structure. And that's also the effect of L over D in laminar case. And this is the 4th one where you can plot dz by dl versus zmm. Okay? So these are different cases as well in laminar, from 2 to 5 to 10, but at different equivalence ratio here of 6. And we can really extract a lot of data from this, and we can extract some correlations. In turbulent cases, of course, if you have a turbulent case, then the these are also maybe 100,000 points, but or clustered in very small region here. So that's how the structure will change, and the code here showing higher gradient in this part and lower gradient in this side. Okay, and this is another one. And this is the effect of L over D for 10,000. And if you go for another case at phi equals 7, you can actually look at the structure. Now you go for the effect of Reynolds number. On this diagram, you can also see the effect of Reynolds number from laminar to turbulent case at certain L over D and certain equivalence ratio phi equals 7. And this is a change. Maybe when you move from laminar to turbulent, you have some sudden change, but within the turbulent, you can see there is not much change here. I mean, once you reach certain level of turbulence, then the mixing is not that much affected by Reynolds number. But of course, when you go from laminar to turbulent, you have quite slight change. Okay, this is also some cases of the effect of Reynolds number. The effect of phi by increasing the equivalence ratio from 4 to 6 to 7, that's also what you can see from these diagrams. Okay. Just moving quickly because we have plenty of data. All right. Okay. What kind of data can we get from these diagrams? If we look at the mixing layer thickness and see, does it really correlate with the stability? I mean, wider thickness or smaller thickness, will that matter? So if we look at that, we can see how can we get that and try to interpret the stability based on this parameter. Then we need to calculate this mixing layer thickness simply by dividing delta Z over the gradient. Then we can get this from each single point, we can get this part and then plot the BDF. So if we plot the BDF for laminar cases, and we can look at this actually here, the effect of L over D by increasing from 2 to 5 to 10. So this is actually 2, and this is 5, and this is 10. So by having longer distance, more time for mixing, then this actually will shift. That means you have a smaller thickness of this mixing layer. When you are at small L over D, you have actually larger thickness. And if you go in turbulent case, you have the same trend from L over D 0, and then L over D 2, L over D 5, and L over D 10. You can see also that the thickness is getting smaller and smaller by actually increasing the mixing time or increasing the mixing length. And you can also look at the mean value of this mixing for cases of laminar and turbulent. So that's versus L over D. You can see the mixing is actually, or the mixing layer thickness is getting smaller. And that's also the standard deviation of this part is also getting smaller, or somehow in the laminar case it's more or less does not change much. So if you look at the effective Reynolds number, that's actually for a certain L over D, okay, from 1000 laminar, this blue line, and for different L over D, you can see that most of them, they are collapsed on the same line. So that means that when we reach a certain level of Reynolds number, there's no much change of the mixing length. And this is at L over D. Of course, it will shift to the left here. And also for turbulent cases, all the turbulent cases do not actually show much change. And this is also from 5,000 to 20,000. I mean, the change is quite small. And this is also the mean value of the mixing layer thickness. And this is a standard deviation. The effect of phi on this, so we keep actually for laminar cases by varying the equivalence ratio. So also you can see the shift from small equivalence ratio to high equivalence ratio. We expect to have more thicker mixing layer. And this is actually for the turbulent case from 2.44 and 6. It's more or less, I mean, it's just getting smaller here, and the tail is maybe getting a little bit thicker. And this also the effect of phi at higher equivalence rate, sorry, higher turbulence, higher Reynolds number, 2, 3, and 7. I mean, more or less quite close. This is the mean value, and this is the RMS or the standard deviation. Okay, so how about if we look at just the boundary of this mixing layer thickness and take the average between this one. So this is the boundary, and the dotted line represents the average of that. Does it tell me something? Let's see. So if we plot the mixing layer thickness versus L over D, you get this type of profile. And this is a stability curve. And we can see that we can have some kind of correlation. By the way, this is very new data. We did not go much deeply in that. But we can see there is something here that tells us we do have some correlation between the mixing field and the stability, and we should actually look at that more deeply and do better analysis of the data and trying to get really concrete theory about this. So another parameter, this will be the last one, okay. So another parameter, which is actually the range of dZmm versus dZ by dL. So we got this diagram that actually shows for all different cases how this range changes. It's, as you can see, it's linear change, by the way, okay? But how these parameters will affect the change. Increasing phi in this direction, that leads actually to higher range of Zmm. And increasing L in this direction, that leads to less actually range of Zmm, and increasing Reynolds number also leads to less. So we move from solid to dotted line here, and to more dotted line that's showing the different effects. If you just follow the legend, then you can actually follow the trend. This is the trend of this part. And then we can look at this versus L over D again. We can see this point if we draw a pyramid, and how this point changing from case to case. And we look at that, the effect of L over D in this point, we can see that this maximum dZ by dL, okay, will be actually decreasing to maybe asymptotic value somewhere when we reach this premixed stuff. So I end up with the conclusions that the stability of the flames is affected by the level of mixture in homogeneity. We know that, of course, and mixture fraction gradient distribution. That's actually very important. Optimum stability was obtained in these IPPS flames, at a certain level of mixture in homogeneity with fluctuations within the flammability limit. And the IPPS mode can improve the stabilization of biogas, which is very important for us to when we would like to move to renewable fuels and low calorific value fuels, and we need to stabilize that. So we could stabilize up to 40% CO2 in natural gas. There is strong correlation between the stability and the mixing layer thickness, as you have seen in the last few slides. And we believe that they developed the 2 and 3 axis diagrams based on this range of mixture fraction, mean value of mixture fraction, and the DZ, or the gradient, are useful tools to describe, understand, and extract quantitative correlations. We need actually more analytical studies are required at several conditions of these IPPS flames using the developed diagrams to extract correlations between stability and mixing field structure. Thank you very much.
So thank you for this very interesting talk on IPPS. I haven't
Yes.
heard that there.
Thank you, Mohy, for a very interesting talk, comprehensive, massive amount of data. So I hope the TNF community takes heed of that, I guess, and adopts it. I have a question and a comment. So the question is with regard to your actual stability mechanism, because in the piloted, the sister piloted burner, it's easy because we have a pilot. So, the ignition source is clear, and there you wait to see the larger number, the maximum number of stoichiometric samples to augment the stability of the flame. And, the mixing and so on is upstream of that to dictate all of this. In your burner, you don't have that. So
No.
you have a recirculation zone. What is the actual stability mechanism in your burner?
Yeah,
so that's my question.
Okay.
And let me add the comment while I have, that is the comment is that it'll be interesting for a burner like this to now migrate to, the cleaner fuels, maybe blends of hydrocarbon and ammonia and so on. Probably hydrogen is as well.
Yeah, that's what we planning for, but I need more students, so that's a problem. Yeah, Asad, thank you very much. This is actually a very nice comment. Actually, there always a comparison between what pilot flame is used for stabilization and what this conical shape is used for stabilization. I told you the cone angle is 52, so this is coming from Faroes, and this perhaps the secret of that. But we did some BIV measurements inside this quartz cone, and we observed this kind of circulation which brings back the hot products into that zone. And that's a mechanism of stabilization for this conical shape. If you remove the cone, of course, you still have some stability, but now the stability is just based on the mixing field. But from one of the slides I shown that the early measurements show that actually this is a level of stability without cone, and this is a level of stability with cone. The cone enhances, yes. Yes, we did. Yes. Yeah. We did that. We did a lot of measurements. We did some of this in Lund with this quartz cone. And we did something in Sydney as well, but not with quartz cone, without, but we did it on the top. But inside the cone, we did OH and also BIV. But I have the data. It's a lot of data. I can show you my publications in this part.
And in the cases without the cone, how thick is your burner? How thick is the tube?
Yes, we have a 12 millimeter diameter, and the inner one is about 8 millimeters.
So how thick is the wall? I mean, is the wall serving as a recirculation zone, or is it a tapered wall?
Yeah, one of them was flat, and the other one we made it tapered.
And
So
do you see any difference?
There is a difference, of course, because this actually thick will make this kind of recirculation. Yes.
Thanks for the quite nice presentation. My question is related to one of your first slides. It's about the effect of the co-flow. I noticed that, and you also mentioned that adding more co-flow increases the stability.
Yeah.
And I was wondering, is it a real improvement or just adding a flow in the outer stream which doesn't burn?
No, no, no. It's a real improvement. And one thing maybe I didn't mention that we measured even the pollution level from these burners with a new technique and with just jet flow, and we found actually a lot of reduction of NO and CO, and it's fully burned. We have this BIV measurement showing actually this kind of recirculation zone at the edge, and you can see the flame is stretched to the outside.
Yeah, so again, I join my colleague in congratulating you for a very nice talk, Mohy.
Thank you.
My question is, so your conical burner, the invert pyramid, maybe I will call it.
That's right.
Would probably compete against swirl stabilized burner.
Yeah.
So can you tell us a bit more about, for instance, efficiency, pressure drop, any attributes to the burner that makes it compete better against the swirl stabilized?
Yeah. Well, yes.
So you have the recirculation zone. I mean, the aerodynamics are somewhat similar because you have the counter pressure gradient, but how does that affect the combustion performance?
Yeah. As I said, that we have already industrial version of this burner from the two, from the circular one and from actually the slot one, and we could actually approach, you know, the range of what we call it, the dynamic range, or for the burner was quite very high. That means you can stabilize the burner at very low load and very high load. And regarding this pressure and dynamics, we did not do simulation yet for this, and hopefully that can help us to understand. But comparing this with the swirl, I believe both they are doing good job, but in our case, maybe it's more simpler for a design for industrial applications. It's just a cone and just put EcoFlow, and that's it. I mean, it does not have too much pressure drop like in the swirl type. In the swirl flame, you need to have more pressure, you need to have a strong fan at the bottom, but for this one, for industrial application, you just, blower can do the job. Because the pressure drop, I believe, is not that high as in the swirl burner.
Okay, well, let's thank Mohy again.